Hello, and welcome to Module 1, the History and Value of Systems Engineering. This module will talk a bit of a brief history of systems engineering leading up to today. Building off of the paper that was discussed in the previous module, we talked a little bit about the history leading up to today. Quote from Rear Admiral Grace Murray Hopper was, "Life was simple before World War II. After that we had systems." While that's a little bit tongue-in-cheek, the reality is systems have always been in place but have grown increasingly complex through the years. So an example of an early specification, going back to the Bible, of one of the oldest books that most people are familiar with, is, "So God said to Noah, make yourself an ark of cypress wood, rooms in it, coat it with pitch inside and out. This is how we are to build it. The ark must be 450 feet long, 75 feet wide, and 45 feet high. Make a roof for it, and finish the ark within 18 inches on the top. Put a door on the side of the ark and make lower, middle, and upper decks." It of course goes on, but you get the concept that these are early examples of specifications. God is giving Noah very clear instructions that the ark must be able to do this. So these are requirements of what that system needed to be able to do, in this case the ark. For other examples throughout history, you look at the pyramids. Egyptians created pyramids many years ago, and they stood the test of time and are still physically in place today. They didn't start by just going and laying bricks. They started by saying, here's what the system has to be able to do, and here's the subcomponents in there, and that's why they were able to be successful. Now, a less than successful version of that might be the Titanic or the Hindenburg, which, while those are examples of systems that were created, those are known through history because they were not so successful in their performance. So prior to World War II, before systems engineering kind of truly came about, architects and civil engineers were really the systems engineers of their time. They were responsible for architecture and infrastructure and had to design components that had to integrate with all different sorts of subsystems. That being true, they also operated without any true theory or science behind it, so their application of these principles was inconsistent at best. During World War II, project managers and chief engineers became more prepared for systems engineering concepts and to truly integrate them to their work. So, for example, queuing theory was developed during this time and emerged as a key component of systems engineering. When you get into the 1950s and 60s, the space race becomes one of the first things that comes to mind for many Americans. This necessitated the quicker development of systems than in the past, specifically because we wanted to get there before our competitors did, which were other countries. While we won't delve into the project management elements of it, these successes of the space program over others were in large part due to successful application of systems engineering concepts. Specifically, project components would be discussed greater detail within the IE452X course. Back in 1962 is where the point where systems engineering specifically transitioned and started to evolve within the commercial sector. Engineering management came into place at that point in time, and businesses and organizations in general of small scope and large scope began to learn from difficulties and failures. The reality is many of these changes did not truly come about until companies had experienced the pain of not having them in place, not having proper systems engineering concepts in place, which led to innovations in practices of engineering, procurement, management, testing, and quality assurance, to name just a few. Driving force for the innovations was also an attainment of high system reliability. Understand that when we talk about reliability, we're not talking per se about the quality of a system, we're talking about how well the system performs over time. So examples that were introduced during this component: material traceability, material process control, a function of quality assurance; change control, so that when updates are made either to products or even just to documentation, so that you could control versioning and know what the change was and why the changes were made, and that you have the latest version available; improved product accountability; and formal interface control. So think about it in today's world. When you have a system that has a failure or any sort of problem, you can go pull up an ID number of some sort, and the company that made it can generally go back and trace to when it was constructed, when it was sold, where it was sold, and have good traceability to what components that they used at that time, and tell whether that could have been part of the reason why the system failed or had the quality problem that they were. All these things were very foreign concepts prior to the 1960s, but are becoming much more commonplace, if not accepted and expected in today's world. One thing that you really need to understand about systems engineering is, while it is one discipline in itself, it is also an overarching conglomeration of numerous disciplines. Some of these include operations research, system modeling, simulation, industrial engineering, risk management, cost estimation, and all those others that are listed there. You could probably list several others in there that aren't included, because the true exhaustive list would be too much to put under one slide here. Software engineering in general today, that's highlighted because that one there is becoming much more critical, and it is truly going through some leaps and bounds from a industry perspective on integrating systems engineering principles. The most important thing to understand here is that systems engineering is a true overarching discipline across all these and some others, sometimes fewer and sometimes more. They are the organization, or the part of the organization, that understands the true trade-offs and integration between these systems elements to achieve the best overall product and or service. Many of these areas look specifically towards their own needs. Operations research, simulation modeling, they look at things within their own individual vacuum, but they may not truly understand the linkages between the specifications or the risk management components. That's where systems engineering comes into play, and that's where systems engineering truly adds their value. So although there are many important aspects of project management in systems engineering, it really truly is much more of an engineering discipline. While systems engineering is quantitative, involving trade-offs, or optimization, specification, or selection, integration of products, they really do need to have their own technical skills and components as well. And that's because if you don't understand what all those elements are, what all those subsystems are, then you can't truly understand how those linkages occur. At the same time, there's also the change management and human aspect, where if you don't understand the design components or the technical aspects of the manufacturing, or the longevity of the materials involved, or whatnot in there, the people who truly do, and truly the subject matter experts, don't trust and respect you to the same level and don't give you the same level of information. At the same time, it is much more difficult to be influential if you don't have the trust of those, not only as a subject matter experts in those areas, but as leadership, knowing that you truly understand the systems and subcomponents that you're talking about. Over the years, many of these standards on the right have evolved, everything from MIL standards back in the 1960s, all the way up to ISO and QS 9000 types of automotive industry standards that are still used today. The reality is, a lot of those MIL standards that were developed in the 1960s still are in place and still are very applicable today as well. And it's important for a systems engineer to not necessarily understand it to the subject matter expert level, but to understand it enough to know how it works and how it integrates in with some of these other subsystems.